Well, good evening, ladies and gentlemen. Thank you very much, Ian, for your introduction and for inviting me to speak to Medico-Chirurgical tonight. I was a bit bemused when I first got your invitation in that I didn't know what I was going to talk about medical, but then I realised, of course, you have a quite wide range of talks in this series, and but there will be a few medical links as we go along, so we'll see how those go. When I saw your programme, I think in the programme it says how we can avoid catastrophic climate change. You'll see my title is in fact a question, not a statement, in that I bring no absolute certainty. What I'm going to do is to give you my personal view about how energy is likely to develop in the future in the context that huge releases of CO2 into the atmosphere are causing anthropogenic climate change. I'm not going to give you a lecture on the science behind climate change per se. I'll give some background to that, but I'm going to take that as read, because I think my belief that with the IPCC, the International Panel on Climate Change, and the research that's been published over the last 20 or more years, that there is now absolute evidence that beyond reasonable doubt that the CO2 being released by us into the atmosphere by our industrial processes is leading to a change of climate, and that this is related to mean global temperatures and what's happening in terms of the chemistry of the atmosphere generally and the physics there. But I'm not going to go too far down that track. What I'm going to try and give you is a feel for how I think we're going to evolve energy and what are the things that we absolutely need to do, and to try and keep our feet on the ground. If we want to do something about this, what must we do that's actually going to make it happen? And a key thing here is that whether you believe in climate change or not, the feeling is that it's somebody else's problem, or that we don't need to do much about it now. Eventually things will sort themselves out. There will be some great technology advances that will enable us to get out of this. And so my basic take-home message tonight is that none of that is true, that I think this is a real concern, that it is, without using too colourful language, it is a war we are fighting. It is a chemical war due to the chemistry that we're changing in the atmosphere. And if this was a political war, or a military war, then the nation would be mobilising resources left, right and centre to do something about it, because it's hidden and its timescales are long, so that the effects of this will not be seen, certainly in my lifetime, the major effects. They will probably not be major in my children's lifetime, but the people I worry about are my grandchildren and their successors. And so I think you have to look at this on that sort of timescale, in that sort of context. So what I'm going to do is to, first of all, just talk to you about what I call the energy landscape, what we currently use for energy and how that's likely to change, and the energy transition, because we've got to move from where we are now, which is still dominated by fossil fuels, to an energy spectrum that is very different in the future. And the key of my lecture is really how do we manage that transition, and a key word there is manage, rather than hope or think that things will turn up. Unless we actually actively manage as individuals, as regions, as a country, and internationally, and this requires great international collaboration, and I'm sure you've followed it in the press of what's been going on with the climate change talks and so on, we will not manage this transition successfully. Now, fossil fuels, I've called that the elephant in the room, because a lot of people say, well, the answer to climate change is simple. We simply stop using fossil fuels. We leave the fossil fuels in the ground. We could do that. There's several things, problem with that. One is as you'll see, to meet our energy demand, the demand of the emerging countries across the world, we can't do it unless we use fossil fuels, and or we revert to an agricultural economy. Another thing is that people think solely in terms of power and heat, electricity, when they talk about using fossil fuels. Of course, fossil fuels provide the building blocks for virtually everything that surrounds us. Everything is made from plastics or chemical building blocks that derive from petroleum and the whole petrochemicals industry. And so again, this device is basically built on oil and gas. There's a lot of electronics in there, but the materials, the silicon, which of course is a different material that we need to harness and nurture as well. But if it wasn't for oil and gas, we would not have the quality of life across the world that we do in terms of construction materials and the things that we depend on for our everyday living. So what I'm going to talk about is how can we manage this elephant, the fossil fuels. My question sometimes when I ask this talk is, can we continue to use fossil fuels and still avoid climate change? And so the green line at the top there says, why are fossil fuels key to achieving a sustainable energy future? And the short answer to that is that we've got to continue using them, but if we use them in the same way that we used in the past, then we will never achieve anything. And then this is not a lecture about my research, but I thought I'd just give you a flavour. A lot of my research is about how we continue to use fossil fuels, but we avoid climate change, catastrophic climate change, I call it, that will make a major impact on people's lives. So I'll just give you a flavour of some of the things, and that's where some of the medical connections come in. And then we'll see how we go. I have a few things at the end, which are about, well, what can we do about it? And I've something on, well, what can engineers do about it? Just so that you know that there's plenty that the engineers out there are working on that will hopefully provide some of the solutions. But also, what can you do about it? Because I believe that everybody on the planet has a responsibility to do something about this. And so the more people that are aware of it, and the more people that can actually stand up and be counted, rather than think it's somebody else's problem, then I think the better we will be off to find a solution. So after that rather long preamble, let me fill in some of that detail. The energy sources, the primary ones we've got, let's have a look at the contenders. You'll be familiar with all of them, I'm sure. In the blue corner we have the fossil fuels, and the usual suspects, oil, gas and coal, that we've been using for, well, this really powered the Industrial Revolution. First of all coal, and then subsequently oil and gas, so going well back a century and a half. And but then those are the conventional fossil fuels, and there's a concern of people who want to continue or realise we need to continue using fossil fuels. Have we reached peak, so-called peak oil? Are we running out of fossil fuels? Well, we've yet to, I think, reach peak oil, so that we've less there than less than 50% in the ground to exploit. But there's lots of so-called non-conventional hydrocarbons. So one that you'll be familiar with is shale gas. This is where all the furor about fracking, and in this part of the world, that, if it isn't an issue now, will become a bigger issue in the future. And there's tar sands. Oil shales, you can get oil in shales as well as you can get gas in shales. And these are much tighter rocks. They're very, very low permeability. And the reason you have to fracture the shale is to create great conduits so that the enormous amounts of gas that are in there can actually remove from themselves from being absorbed on the rock and come into these channels to get them to the surface. Tar sands are rather like what it says. It's the stuff. This isn't a liquid. This is a solid. This is the stuff that we put on roads. And asphalt gets its name from the chemical asphaltenes that are actually the heavy hydrocarbons that are in those oils. And then there's gas hydrates. Very, very interesting. These are ice-like structures that contain methane molecules in the middle of ice crystals, ice-like crystals. And there's a lot of this in the sediments that are fairly shallow. There's a lot in the Far East around Japan, and in Arctic conditions. So in Siberia, the Russians have exploited a lot of gas hydrates, and there's more gas in gas hydrates than in the whole of the other gas sources in the world. The problem is that, as I said, you get these in shallow sediments, a lot of it's under the sea. And the hydrates act as the glue that keep the rock together. And it's a bit like taking the top off a champagne bottle, the cork off. As soon as you release the pressure to release the gas, then the rock starts to fall apart. And so you can get tsunamis, you can get subsea volcanoes. So the trick here is, how can we get these enormous supplies of gas out of the ground without actually causing major geological faults and problems? Now, I've mentioned gas several times, and one of the keys to using fossil fuels in the future is that because gas is CH4 mainly, and most of the oil, once you get beyond ethane and you get to coal, then it's CH2, and coal is essentially CH. So the number of molecules of CO2 that are released when you burn methane for the same energy content is 50% of the CO2 that comes from the same energy release from hydrocarbons, oil, or from coal. And so gas is not completely clean, it's not as renewable, it's not sustainable, but in terms of CO2 release, it gives you 50% less. So if we could convert everything tomorrow from using oil and coal to using gas, that would be a big step. And we can use that for heat, power, and for chemicals. You can make all the chemicals that we want to now from gas, as well as you can the usual oil and that for feedstock. So let's bear that in mind. Gas is part of this solution. Then in the middle, in the red corner, we have nuclear, and we have fission, which is our traditional nuclear energy that we've been having the benefit from for 60 or 70 years. And we have conventional reactors that have had their problems in the past, and then we have advanced reactors that there's rapid fast cool reactors, there's pebble bed reactors, and you've probably heard about smaller nuclear reactors, more localized reactors, modular reactors. All of these produce only about 5% of the nuclear waste that the older reactors like gas-cooled reactors, pressurized water reactors produced. The problem with nuclear, and I'll come to this later, is that there's all this so-called legacy waste, that the less efficient earlier reactors have produced all this nuclear waste from the spent fuel rods that still has not been, in this country at least, disposed of safely. So it's in temporary storage in Sellafield, and the government is gradually finding ways to put this into more permanent storage. But the fact that modern reactors produce very little waste, and that could be dealt with much more easily, is blurred by this legacy waste, where there's concern that nuclear energy produces nuclear waste, that, as well as the worries about the safety of the reactors. I'll come to this later. And then the other form of nuclear energy is fusion, where you take helium and fuse that and release energy by nuclear fusion. Now, nuclear fusion is about 35 years away, people say, but it's always been 35 years away, and probably always will. You denote a hint of cynicism there. Progress is being made, and I think if we did find a way to actually sustain fusion at scale, this would be a revolution in the way that we could supply energy. But I don't think, in terms of the timescales I'm talking about from where the research is now, that that's actually going to happen. And then, of course, in the green corner, we have the renewables. sources of energy that either do not emit CO2 or other greenhouse gases, and we shouldn't forget other greenhouse gases, or very, very small amounts. For instance, biofeedstocks. Here we're using photosynthesis to produce plant materials, and there are various ways we can convert these to power, heat, and to chemicals. Waste is part of that. There's hydroelectric, which is very geographically dependent, where people have got high drops in potential energy as a way of storing and releasing energy. There's wind, and the UK has invested a lot in onshore and offshore wind in the last decade. Wind's a good example of where to say something is completely carbon free is not true, of course. If you look at the construction of wind turbines, a lot of energy is needed, both to extract the raw materials and to fabricate the wind turbines. So you have to make sure that when you're choosing the spectrum of energies you're going to use, that you don't actually choose the part that fits your argument, but you do a cradle to grave, a whole systems analysis to make sure that you've taken into account everything that's relevant to that particular form of energy. Wave energy. A lot of energy in waves, and there's a lot of energy in tidal. And Swansea, you've heard recently about a lot of publicity about the tidal lagoon in Swansea, where we have some of the highest tides in this country of, is that 11 metres off Swansea Bay, where that's going to provide enough electricity for 150,000 homes if that project comes to fruition. And so I think in this country we've done a lot with wind, but maybe not as much with the water energy that we have. And then there's geothermal, getting the energy from the core of the earth, where again there's a lot of heat energy there that we can extract, and some countries have invested in that. And then, if you like, the jewel in the crown is solar. In fact, all these energies are solar. The source of everything that we've talked about comes from the atmosphere, and the fossil fuels have arisen because of they're an intermediate energy carrier for solar energy, and because they've originally originated from either plant or animal material. Now solar, there are two forms. One, you can actually focus the sun's rays and concentrate the heat in terms of heat carrying fluids, and that's probably more advanced than photovoltaics, which is where you take solar energy and using photovoltaics silicon technology, you convert that into electrons and electricity. But there's an awful lot of energy in the sun, and the problem there is that our ability to convert that into heat and power particularly is not very efficient. And so that's the key thing there. What is the cost of actually being able to create enough electricity at the relatively low efficiencies that we have now? So I've summarised all that in this energy landscape, where currently the world consumes about 15 terawatts per annum. And I've got fossil fuels in the middle, which consists of about 80% of the energy the world uses. And then we've got these others that I've talked about dotted around the edge. And I've put on there either the current capacity or what estimates, the best estimates we can get of, given the limitations on land, say for biofuels, or there's a similar limitation on land in terms of where we put wind farms, and that's one advantage of offshore wind, but it's much more expensive to put things offshore. And so using abandoned oil platforms is one good way to actually exchange one infrastructure for something else you need. But the simple message of this slide is that there's no one of those, apart from solar at the bottom, is going to replace fossil fuels in terms of volume of energy realistically over the next tens of decades. And so we've got a spectrum, a landscape now of energy in this country. We use a lot of fossil fuels, but we use increasing amounts of renewables, and we use nuclear. This is going to continue to be the case over for the rest of this century, as far as I can see. So we can't find a single golden bullet that's actually going to deliver it. So when people say we must change to renewables, we've got to actually selectively change to some combination of renewables, and that's going to be very geographically dependent. So there are some countries that are well on the way. New Zealand, for instance, I was surprised when I visited there when I was IChemE president, that being president of these organisations gives you lots of opportunities that you wouldn't otherwise get. And I've interested in some amazing places and saw some amazing technology and met some amazing people. And in New Zealand, 70% of their electricity is renewable. And they have a lot of bio, they have a lot of hydroelectric. And if you take France, of course, they've got 70-80% nuclear. But next door, Germany, following the Fukushima accident in Japan, 2011, they banned nuclear, but they still use French electricity, I understand, so I don't know how they square that. But the message here is, solar, 36,000 terawatts on land. If we can just increase our efficiencies from, say, 5-10%, the best devices now, to getting up towards 50%, this will start to be very competitive. And the thing we have to think about is how do we replace what do we do about the materials if we're not going to use fossil fuels? Well, we can use bio feedstocks, so we use biological feedstocks. And the thing about biological materials is that they can become, they're at least carbon neutral, roughly, in that we've used carbon dioxide from the atmosphere to create them, and they're simply releasing the carbon dioxide when we use them. You can go from solar to chemicals, and there's a lot of good research going on in this, in that just as you can go from solar through devices to electrons, you can actually go from solar with photocatalysts all the way to fuels. And I'll tell you a bit about some research I've been doing in that area later. But it's not the solution for next year, it's the solution for about 2070 or 2080. Because one thing people often lose sight of is if something's in research now, to get it industrialized and up to capacity and scale, having worked in the oil and gas industry, I know that some of the embryonic technologies that were there when I joined the industry in 1985, when I left it in 2005, were just about coming up to scale. So the time scales are decadal in terms of getting this stuff into the market. And where we are in terms of renewables now, this slide's a bit old, but it's not too different than that now. About 13 to 15% of the energy globally is renewable, sustainable. And a lot of that is bioenergy. There's geothermal, and you can see solar is very small. Now, solar is the fastest growing renewable energy, but it's starting from a very low baseline. So it's not going to get there very quickly, as I'll show in a minute. So on top of what I've shown you, where in order to meet today's demands, we're using 80% fossil fuels. If we look at the future, there's some major drivers that say that the energy consumption of the world is going to increase. Despite all the calls for us to be more caring and efficient with the use of energy, the world population is going to go up from 7 point something billion now to about 9 billion by 2050. And you can see from the plot there that most of this growth is going to be in the non-OECD countries, the countries that are developing their economies. And we could say, well, you can't use fossil fuels, but we've got to where we are using fossil fuels. To say to these countries that you can't use fossil fuels to actually fuel your economy at the point where you're expanding your education and industrial systems is, of course, not going to work. And one of the challenges of the Paris climate change talks was how do the industrialized countries help the emerging developing economies to actually meet these targets through a combination of aid, technology, and, if you like, phasing it so that the industrialized world takes the hit first and lets the other countries catch up before they have to do the same. And so linked to that is this major economic expansion of the BRIC countries in particular, but the non-OECD countries in general. So the projections are that world energy demand is going to at least double by 2050. So by 2050, instead of having 15 terawatts, we've got of order 30 terawatts that we've got to find. Given the restrictions on how much we can produce from the various renewables, you can see that this is a goalpost that is getting more and more difficult to attain all the time. So the problem I've described is often described as the energy trilemma, because in order to do something about this, what we've actually got to do is for any given community, we've got to try and achieve at least three things. We've got to have energy that's affordable. We've got to have less and less carbon emitted, and we've got to have security of supply, because this means if you've got to import energy from other countries, A, it's going to be more expensive, and B, you have less control over the ability to supply the energy in the first place. You know, our gas in the North Sea is running out, so we import a lot from Norway, and we have tankers of liquid natural gas coming all the way from Qatar to South Wales to deliver a lot of the gas that we use. And that's very expensive. And so people worry about us exploiting our own shale gas, but that's probably going to be cheaper than some of these other solutions, even though there are issues that do need to be addressed. So squaring this triangle of how do you actually achieve all these at the same time is the great challenge both to technologists, engineers, but also to politicians and policymakers. Because the bottom line is that to do something about reducing the amount of carbon we have in the atmosphere, whether we do it by changing the way we use fossil fuels and basically capturing as much of that carbon before it's released, or we use renewable energy, which are emerging energy, forms of energy, at least at scale, all that's going to cost more. And so the affordability issue is the big political hot potato that in order to do something about carbon mitigation and sometimes about security of supply, the message to the consumer is, I'm afraid you've got to pay more for energy. And that's not a very easy thing that politicians like doing. So it actually acts as a brake on doing much about actually addressing these issues. My message tonight is that there's no free lunch. If we want to do something about climate change, whatever mechanisms we choose, we're all going to have to pay more for energy. We're going to have to pay more, whether it's through a carbon tax or the way this is built into the system, that prices go up because we're using alternative forms of energy. Well, the driver of this, of course, is the increase in mean global temperatures, which we see on the top right there. And this is linked to the amount of CO2 in the atmosphere in parts per million on the bottom right. And the top, sorry, your left, my right. And the top right shows the exponential, more than exponential rise of the CO2 levels in tons of CO2, gigatons of CO2 per annum that are emitted into the atmosphere since the Industrial Revolution. And sometimes we'll talk in terms of carbon, tons of carbon, sometimes CO2. So if you just divide roughly by 4 the amount of CO2, you get the tons of carbon. So we're at about 32 tons of CO2 per annum released globally now, but 8 gigatons of carbon. As I say, I'm not going to debate that. I think the evidence that there's a causal relationship is strong. But if anyone challenges me on is climate change a reality, I would say that even if it wasn't a reality, all the things that we need to do in terms of good husbandry of our resources need to be done anyway. And if we're not prepared to pay for it for climate change reasons, then for the future generations in terms of actually making best use of the Earth's resources, we need to do it anyway. So this is a projection of how global temperatures are likely to increase as carbon emissions increase over the next few decades. The top red line is business as usual. If we do nothing now, in around 2000 we were around 375 parts per million of CO2 in the atmosphere. It went soaring through 400 in May 2013. And if we do nothing, then it's going to be at about 1,000 parts per million by 2050, and the consequences of that are a mean global temperature increases of 4 to 6 degrees, which will be catastrophic. So in my title, what I mean by catastrophic is that we will get rises in sea level which will wipe out a lot of coastal areas. You will get increase of desert regions. You will get melting of polar ice caps. You will get necessary migration of humans. You will get the consequences for agriculture and for the animal population will be major. And the consequence of this will not only be, if you like, geographical in terms of migration or whatever, but there will be a lot of social consequences of this in terms of the cost and the unrest that arises from that. So, I mean, this is political dynamite in terms of how you run communities if this is going to happen. So how do we avoid that? Well, we need to keep that ideally below 400 parts per million, but as I said, in 2013 we passed that deadline. So by the best estimate of an achievable target now is to keep it, it's about 400 and something now, to keep it below 450. And the Paris Agreement, where there was an agreement to keep it, if possible, to 1.5, but certainly to 2, and the 1.5 was driven by smaller island communities, which are the most vulnerable to the rises in sea levels, and they have them, are going to be the early sufferers of generalized climate change rather than sporadic that we see now. If we can keep it to 450, then 2 degrees is still not negligible, but we can probably, with mitigation measures rather than with adaptation measures, so adapting to the fact that it's gone up, we can probably cope with that as a global community. And of course there's an economic cost to this. We have the Stern report in the early 2000s, which said that it's cheaper to do something about climate change sooner rather than later, and if we do something about it now, to do some of the things I'm talking about tonight, it will cost us 1 or 2% of GDP, and the longer we delay it, the greater the cost. And Gordon Brown commissioned this report. It had a lot of publicity at the time, and it's essentially now dead and buried. And it's interesting that at the time, it had a lot of publicity in that this made people sit up and take notice. But the major thing that happened was that people started to pull holes in the economics of the report, which was almost like the climate change deniers, in my opinion, trying to pick holes in the climate change evidence, because this was not something people wanted to hear. Rather than, in a way, all these reports have error bars in them. The underlying message was that if we don't do something sooner rather than later, it gets more expensive and more difficult. And 10 years later, we've done hardly anything that wasn't in place then, comparatively speaking to what we need to do. 550, some people think, is the sort of halfway house that we could settle with, but that, I'm a born optimist. I still think we can meet 450. Well, you look at scenarios of energy use going forward, and this is a sort of middle of the road. You can take your pick of all the International Energy Agency and IPCC scenarios going forward in terms of low carbon future or business as usual. This is somewhere in the middle. But this indicates this goes to 2030, but the percentage doesn't change very much if you go out to 2050. You take those bottom 3 bars, we're still going to be using, by the middle of this century, about at least 50% fossil fuels in order to meet the global energy demand that I've talked about. We will get a growth in renewables. I think nuclear will grow faster than it's shown on that graph, but we're going to get this vast increase in demand, and so even though we use less oil and gas in absolute terms, the proportion is going to be still of order 50%. Now that dotted line there, that's a good indication that there are financial levers that you can pull if you want to do something about this to control, say, energy demand or energy use or energy costs. That dotted line is what would have happened if we hadn't had the global banking recession in 2008. And so the world economy had a big shock then. So this was not deliberate financial control. This was an unintended consequence of what happened with the banking problem. When world economy shrank, there was a lower demand. And so you can see that that had a really significant effect on the energy demand. And one thing I'm going to say in a minute is that controlling demand and getting people to use less energy or to use energy efficiency, I believe, is the lowest hanging fruit, the best lever we have to do something in the short term. I've said that we're not going to be able to replace fossil fuels as quickly as we would like. If we could bring them in tomorrow at comparable costs, nothing would give me greater pleasure. I think we should try to bring in renewable energies as fast as we can, but we've got to make them affordable and we've got to make them available at scale. And so this is some of the factors that are going to limit that growth. First of all, I've talked about the slow rate of transfer from embryonic technologies into large-scale energy-providing commercial concerns. And that's decadal, and a lot of the things that we're talking about, I'll show in a minute, are still on the development curve. And we've got to, compared with that, we've got to bring costs down as we bring the scale up and make the costs comparable with fossil fuels, because at the end of the day, unless governments are prepared to be interventionist, then at least in the Western world, a lot of the Ocean Pacific world as well, it's the market that drives things. And if governments are going to rely on markets, then I don't think we'll solve the problem. But at least we've got to try and make the economics work so that the cost curves cross and the sustainables and renewables become cheaper than the fossil fuels. We don't add the cost of carbon capture and storage, the technology I'm going to talk about in a minute, to take the carbon out of the fossil fuel use where it's used centrally, where we can capture the carbon. And that adds probably about 25% to the cost of electricity. And so where we're comparing costs, today there's a hidden subsidy of fossil fuels, which is we don't really build in the cost of taking the carbon out. In my view, we've got to continue to use fossil fuels, but we've got to take the carbon out where we can, and we have to add that to the real cost of using fossil fuels. There's the availability, and I've said that a lot of these alternatives, that there's capacity problems to do with land use or raw material resource. The biggest problem is coping with intermittency. That most of these energies are intermittent: wind, solar, tidal. So we get bursts of energy when these things are high, and then we don't get energy when the wind doesn't blow or the sun doesn't shine. And so unlike fossil fuel power plants and nuclear power plants, which can be ramped up and down very quickly and provide steady levels of energy, we can't use intermittent energies in the same way. That's because we can't store them. Now, we've got better at storing electricity over the years, and the whole of our lives are now dominated with these things. I use this for several illustrations in my talk. And lithium-ion batteries and storage, even though we all complain about the lifetime of all the charge time of our batteries for our iPods or our phones, that has gone through quite a revolution over the last decade. But what we're not good at is storing electricity at the gigawatt scale, which is what we need to do. That's the power station level. Batteries and storage devices or supercapacitors that will actually store the energy so that we can produce it but only release it when we need to use it, and what's going to make a revolution in terms of how we can use renewables. And again, that technology is embryonic. And then I've talked about nuclear, that there are a lot of reasons why countries decide not to use nuclear. The technology, I think, is address a lot of the safety and the disposal legacy issues, but it only takes one accident like Fukushima to set the industry back a decade maybe, and the continuing concerns about proliferation. So nuclear, I think, will continue to be contentious and patchy. The other thing about nuclear is it takes 10 years to get a nuclear power station on stream, and we're going to suffer from that because a lot of our nuclear power stations coming out for decommissioning, and with all the furore with EDF and the Chinese funding of our new nuclear power stations, we're going to go through a dip in nuclear capacity in this country that we've got to make up from somewhere else. So this is just to take, I've taken biomass for fuels and heat and power. And this is 4 generations of biomass, and what I've done here is to plot the maturity of the technology compared with where it needs to be in 2050 to meet some of the targets we're talking about if we're to provide some of this energy by renewables. And you can see that some of this is quite mature, so fermentation processes and using wheat, sugar beet and producing fuels. Ethanol, so Brazil has quite a low carbon footprint because it has a lot of hydroelectric and uses sugar beet for alcohols for fuels. Likewise in the States there's been some move to use wheat for ethanol. That's quite mature. The second generation is to be able to use lignomaterials, lignocellulosics, the non-crop cellulosics, and to use the waste material from food so that it's not competing with food, it's using the waste material, and to use waste material in general and to use energy crops like miscanthus. And Fischer-Tropsch is the means by which you then you gasify the biomass and you convert this to chemicals and the materials that we use for manufacturing artifacts. The third generation is algae. I'm a great fan of algae. I've done some work on green algae myself. That these little beasts, you can get energy from them at all stages of their life. When they're alive, they're great photocatalysts that can convert water to hydrogen and CO2 to alcohols as fuels. And then when they're dead, you can actually extract bio oil from them. There's a lot of lipids there that you can extract, so-called alg oil. And then when you've got the husks, you can burn them. And so they're very useful, and they have the advantage that they replicate very, very quickly. So the land mass you need to get the same amount of biomass compared with growing energy crops, so you can get factors of 10 or more increases in land efficiency if you use those. So I think they may form a part of the bio future, but they're still in the early stages of development. A lot of this is still very small scale. And then the final generation of things that include solar to fuel. So going, rather than, you go all the way from solar energy through photocatalysts to fuels and chemicals. And some pyrolysis, more sophisticated ways of treating biomass that may be more efficient. So it's just to show that there's lots of ways we can get energy and materials from biomass, but they're several decades, most of it, away from commercial scale and cost competitiveness. I've just put at the bottom there, of course, that if we use biomass for energy and we take the carbon out, or we use the biomass to create plastics, materials that stay in the built environment for decades or centuries, this is a way of actually taking carbon out of the system. And so since photosynthesis has taken the CO2 out of the atmosphere and we're not going to release it, in potential this is one of the few technologies that can be carbon negative. And I believe it's the only technology that can do it at scale. So if we really, rather than stopping releasing CO2 and levelling off the CO2 levels by lowering the rate of increase of release, we need to suck CO2 out. Nature does it best with photosynthesis, and this is a way to actually make sure that that stays out of the system. So this was just a bit more detail on those several generations. The other example I want to give you is solar. So it's the fastest growing renewable energy, but if you look at this roadmap from the solar industry, you can see there that their projection is that by 2050, this is the percentage of electricity that will be generated by PV. They reckon that only about 11% of global energy will be, electricity will be produced by PV in 2050, and that's the industry's projection itself. So it's starting from a low level, it's growing by tens of % a year, and the efficiencies are improving all the time, but to actually make an impact, maybe it's going to be 20%, but it's not going to be the 80% that fossil fuels is now. So this just shows a whole range of technologies that are on this learning curve to where they need to be in 2050 to deliver what we want to. The key thing is they're not there now. And where they are there, if we want to use them at scale, they're very expensive. And that's the key issue. So I go back now to a more sophisticated version of that CO2 versus time plot I drew earlier. The top part of this curve is the CO2 levels in the atmosphere if we do business as usual. That's the 1,000 parts per million one, out to 2050. And the bottom of this plot is the 450 parts per million curve that we're targeting. And you can see that in 2050, if we don't do anything, we'll be releasing 62 gigatons of CO2 a year. Well, this is a model, so it could be plus or minus 5 or whatever, but the numbers won't change the argument generally. If we are to actually achieve this 2 degrees limit on global temperature rises, by 2050 we've only got to be emitting 14 gigatons of CO2 a year. So that's roughly the difference, about 50. So what we've got to do by 2050 is we've got to not release 50 gigatons, that's 10 to the 9 tons of CO2 every year that we would be releasing if we didn't change our behaviour now. So that really puts it in perspective. This is an enormous challenge. And what these different colours tell you is what different mechanisms can you use to achieve that target. And if you take the blue and the yellow at the bottom, that bottom 50% is essentially things to do with energy, improving energy efficiency, using less energy, and fuel switching where you can. So for instance, going from oil to gas or coal to gas. So 50%, 25 gigatons we can achieve by that. And I reckon that's the low-lying fruit. The technologies exist there, and some of this is merely a matter of changing behaviour or providing incentives to change behaviour that compared with what we do now, rather than relying on people's altruism and desire to change the planet off their own bat. The next 2 bars are nuclear and renewables, and that's about 30%. So another 30% of this 50 gigatons we will not release because we've swapped to renewables or we've got more nuclear. And it may be more than that. On the other hand, it may be less than that. We've got to do all of the below to actually reach this target. Now the top, the orange and red is using CCS, carbon capture and storage, with power generation and industrial processes. And that's 20%, so that's 10 gigatons, 20% of this 50 gigatons, we've got to actually take out of the system by continuing to use fossil fuels, but capturing the CO2 where it's used centrally in power stations or manufacturing plant. So we haven't got to take all the CO2 out of the system that we use fossil fuels for, but we've got to take out that much. And I'll show you what the challenge of that is. My message here is that energy efficiency is absolutely key. Renewables and nuclear absolutely key, and we grow those as fast as we can. But given the moving targets of global energy, we won't achieve any of this without we have complete deprivation of the lifestyle that we have today, particularly for emerging countries. And we need to continue to use fossil fuels to do that, and we can't continue to use fossil fuels the way we are now. We've got to take the carbon out as much as we can. And that is by this process of carbon capture and storage, and many of you I'm sure will have come across this process where it's produced, you actually, in the gaseous emission streams, you absorb the CO2 in solvents or on solids to take it out of the system and stop it being released. You also want to stop methane being released. And this is why if we use more gas, we make sure we don't have too many gas leaks, because methane is 20 times worse than CO2 as a greenhouse gas. It lives has a shorter lifetime in the atmosphere, but it's 20 times worse in terms of global heating capacity. What you then do is you transport this CO2, you compress it to a liquid or a supercritical fluid, which is at a higher pressure than a liquid, but it has the properties of a gas but the density of a liquid, and that makes it easier to inject into things. But if it's a low viscosity as a gas, but high density, you want it for storage. And then what you do is you inject it into storage sites, geological storage sites, and there are three types. One that's not given much publicity is unmined coal seams. There's a lot of methane, as you probably know, in coal seams. This was all the problem with canaries in coal mining over the ages, is that a lot of methane absorbed on the coal. You can in fact inject CO2 into those coal seams because they're very fractured and got enormous surface area. You can store more CO2 in a coal mine than you can in an old oil and gas reservoir. And at the same time, you can release the methane, which is the cleanest fossil fuel. And so it's methane you wouldn't otherwise be able to get because the CO2 prefers to absorb to the coal. It's got a stronger affinity for the coal than the methane, and so you release the methane at the same time. Oil and gas reservoirs that you've taken the oil and gas out of, they're replaced by water, and then you can displace that water with CO2 to store it as this supercritical CO2. And deep saline aquifers, which these aren't the aquifers that we use for drinking water. These are several kilometres deeper, and these have never been used for anything, so they're not geologically characterised, so it's more expensive to characterise them, but the capacity there is enormous as well to put the CO2. So the estimate a few years ago now is that more than 20,000 gigatons capacity to store CO2. And if you remember, I said we needed to store 10 gigatons. So this is, at that rate, 200 years capacity. And if we haven't solved the problem in 200 years, we won't be here. So I don't think there's a problem about having the capacity to store the CO2. What we need is, and we've got the technology, we need the political will to do it. Well, there are projects. There's Sleipner project in the North Sea. So this is the oldest project at scale. 1 million tonnes of CO2 have been injected for the last 20 years in the Norwegian North Sea. And why was this? It's because the Norwegian government were the first in the world to introduce a carbon tax. And so it was cheaper to inject the CO2 than to release it and pay the tax. And so this shows the power, where governments have got the political will to do it, of how political monetary levers, financial levers, can drive the process. This is the most modern, or the most recent CCS project, Boundary Dam in Canada. And it's the first one that's described as truly commercial, in that it's driven by commercial factors rather than tax or subsidy or making a loss. And this is also 1 million tonnes a year. And the driver here is that you can actually inject the CO2 into nearby oil and gas reservoirs and recover more oil and gas. So this is enhancing oil and gas recovery by storing more CO2 in there. If you actually do the balances, you find that in fact, although you're producing more oil and gas, it's net CO2 negative, so that you actually, even though you release more gas that to use, that overall in the cycle you generate far less CO2 than you would if you didn't store it. And this has been on stream for about 2 years now, and just to give you a feel, that 1 million tonnes of CO2 is the equivalent to taking 250,000 cars, probably Canadian and American cars, off the road. There's another technology that people will talk about, which is carbon utilisation, carbon dioxide utilisation, CDU, which is using catalysts to convert CO2 as a feedstock into materials, particularly plastics, urea. There are certain and carbonate inorganic materials. You're going uphill thermodynamically here in that you need to put energy in unless you have some very clever catalysts, and nature has some very clever catalysts in the form of some of these green algae. But the major problem of this is if you were to replace the whole of the chemicals supplied today by using CO2 as a feedstock rather than oil or gas, you would still only use about 2% of the CO2 that we need to store. So this is a very clever technology. It will have its place in terms of using a waste material, but I believe it's not going to actually make a substantial difference. And people say, well, it's very unimaginative to store CO2 under the ground and to keep it there for centuries. Let's do something with it. Well, this is a way to do something with it. It's more creative, but it's not, I'm afraid, in volume terms, a solution to the problem. Another potential solution that we're working on at Imperial College is, instead of actually bringing everything up to the surface, you leave as much underground as possible. So you do subsurface processing. You do a lot of the processing we currently do in oil refineries under the ground. You take the CO2 out from the system under the ground, you leave it there, use the low value hydrocarbon, which you don't use a lot of, you only use the light stuff usually, and you actually then produce fuels like hydrogen, methane and methanol. You can produce heat and electricity from the processes subsurface, and then you produce all your chemicals from a combination of carbon monoxide and hydrogen, which is called syngas, which actually has a lower carbon footprint than using naphtha, and processes exist for that. But this is a paradigm shift. To do this will take decades, but I believe we're going to use fossil fuels for the rest of this century. And if we really want to actually make a difference, instead of actually putting a lot of energy in to get the hydrocarbon out, and the heavy hydrocarbons, the non-conventionals, take more energy, a lot more energy to convert it to things, a lot more energy to take the CO2 out and then bury the CO2. Let's leave the CO2 underground. So, to achieve what I'm saying is a low carbon future, but using fossil fuels, a low carbon fossil fuel future, I've summarised on this slide what we need to do. Use less energy, use more gas, capture as much of the CO2 as we can, use more nuclear, but that's not a rapid solution, and go from fossil fuels to a portfolio of renewables as quickly as possible. But my belief is that this is decadal. It will take more than 50 years to make that conversion. So if we don't do something about the CO2 from fossil fuels in the meantime, it will be too late to actually use a lot of these other technologies. And I believe to drive all that, we do need an effective carbon pricing system. Very few countries in the world have done what Norway's done and put a tax on carbon. And there are various ways you can actually put a price on carbon and make sure it's built into the, so that the driver, you only get to people in the end through their pockets. And this would be a way to manage the energy transition to 2050 and beyond. So Paris was a great triumph in that it agreed, at least 196 countries agreed the targets, but it did nothing at all about mechanisms. And until we actually translate those targets into mechanisms, it will still be an aspiration. So please don't feel a little short-term good about Paris, but then question your politicians about what are we doing. And it took Britain until long after Theresa May came into power to actually sign the accord, some almost a year later than a lot of other countries did. So although we've got a Climate Change Act which builds reduction of CO2 to 80% of pre-1990 levels in law, one of the few countries to do that, so that's the good side. We've actually got to put our money where our mouth is, if you like. I'll get off my soapbox in a minute. So the problem, that's what we need to do by 2050, but the problem is where we are now. If we don't start to do something about this now, these will be moving goalposts. So if we delay this 10 years, the amount that we can take out by energy efficiency and renewables will go down. So the amount of fossil fuels we have to use will go up. So the target won't be 10 gigatons, it'll be 15 or 20. So that's why time is of the essence. How are we doing? 1990, 2.39 tons of CO2 per ton of oil equivalent released globally. 2010, the figure hadn't changed very much. Now, there has been some improvement since, particularly the US had this enormous shale gas explosion, used far more gas and replaced coal. And in fact, the levels, rate at which CO2 has increased since then, because the US is such a big energy user, has actually shown significant improvement. So that's a foretaste, I think, of what we might do simply by changing to gas from coal and oil. But I think in a non-CCS world, where we continue to use fossil fuels without doing much about the carbon, then we're not actually doing much to meet these targets. Now, there is some light at the end of the tunnel. You can see that in the last 2 or 3 years, this curve of CO2 emissions per annum against time is sort of levelling off. And for the first time In 2014, the latest year for which we've got all the figures, emissions actually went down. They only went down 0.2 of a gigaton. You may say that's in the noise, but at least it's going in the right direction. And this is the first time that it's happened despite economic growth. I showed you that earlier we'd reduced consumption because there was economic recession. But in a time of economic growth globally, of 3.1%, we've had this decrease. So things are happening, but they're happening very slowly. And these are the number of CCS projects in the world. Most of those are fairly small scale. There's only about 20 that are at the 1 million tonnes a year. So 1 million tonnes is 1,000 times less than the gigaton. So if we're only got 20 megatons compared with the 10 gigatons we need to take out in 2050, you see that's an enormous challenge. And what this slide shows is that by 2050, to meet this target of 10 gigatons per annum, we've got to have over 3,000 such projects, and we've currently got about 20. So this means that in order to do, it's doable, but we've actually got to move at a hell of a rate to do it. This is 100 projects of that size per annum from 2020 onwards. Incidentally, I should have pointed out on the CO2 slide earlier that, just to personalise it a bit, that each one of us in this room, on average, in the UK, we produce about 10 tonnes of CO2 a year. So that's a figure to bear in mind. In the States, it's about 18 tonnes per person. But rather than seeing these things as things that happen in industry and power, we're all responsible because we all use it. So I use 10 tonnes of CO2 a year. I'll come back to that later. In the UK, the changing face of our energy mix is improving. In 2016, you may have read in the press, this was the first year where wind exceeded coal as the percentage of our electricity generation. So, things in terms of decreasing the dirtiest fossil fuel, coal, in terms of CO2 terms, is moving in the right direction. And wind, which has huge subsidies, is the way that we're doing that, plus a conversion of some of the coal to gas. So you can see that the UK, in fact, is using less energy overall. It's falling down on the right-hand side, and our yellow renewables content is going up. And we're doing this because we have these targets set in law. This is what's in the Climate Change Act, to go from 800 megatons of CO2 equivalent released in 1990 to down to 124, a decrease of 80%. That's what's built in. And the way we're doing this is every 2 years we have these carbon budgets. So this is the nearest we get to Mao Zedong's national plans for our energy. And one of the problems at the moment is that we are meeting those targets by doing what we're doing at the moment, which is basically to put some subsidised wind or some subsidised solar in to make some conversions to gas. But it's accepted that we will not meet the later energy targets unless we actually put CCS. Even when we convert to gas, that's not good enough. It still emits CO2. We've got to take the CO2 out of the gas with CCS. And so you can see that on this curve here, which is the latest from the new department. The Department of Energy and Climate Change was replaced by BASE, Department for Energy Innovation and Industry. And the top curve there shows that, in fact, renewables will grow from about up to maybe 50 megatons of oil equivalent a year. But oil and gas, the bottom line, will stay at about 3 times that, 150 over the next few decades. And the major difference there is phasing out solid fuels, mainly coal. So the figures from the ministry show that, in fact, we're still going to continue to use an awful lot of fossil fuels. That's why it's very disappointing when the 2 projects that we had in this country, this is the Shell SSE Peterhead project, and we had another one, the White Rose project, closer to here, run by Alstom and Drax and BOC and the National Grid. These, between them, would have stored 2 million tonnes of CO2 a year, but were the springboard to actually having scale up to commercial level, and then creating a CCS business that could be as big as the oil and gas business, as my figures show. These projects were cancelled in the autumn statement of November 2015. So despite the fact that to meet these later carbon budgets, to save £1 million now, these projects were cancelled. The technology learnings will be used in other countries, and we, if we want to meet these carbon budgets, have got to introduce some carbon capture projects from scratch, if you like. It's not only altruism and buying time. There are studies that show that if we don't implement CCS, the cost to our economy by 2050 will be the order of 30 to 40 billion pounds. So it doesn't even make sense in terms of overall cost terms. We will have to pay more for electricity in the short term, but that's nowhere near as much as we shall have to pay in the long term. And this is the problem with a problem that we have to deal with now that can be put off, and the sufferers from it will be future generations. A similar study in the States showed the same thing. Now I'm going to have to wind up a minute, and in a minute I'm not going to cover everything that I was going to talk about, but another chink of light is that people have started talking particularly from government recently, about one way to decarbonise our heating systems is to use hydrogen. And Leeds is being talked about as a prototype hydrogen heating zone. In order to produce the hydrogen, you have to produce that from gas. By reforming of gas, you produce hydrogen carbon monoxide, you convert the carbon monoxide to CO2, and then you've got to store that offshore. But the hydrogen can then be used for renewable electricity, or it can be used for heating. And Leeds, there's a project by Northern Gas and Partners that's H21 that's looking at investment to try and do this prototype project. So maybe carbon capture and storage can piggyback on other drivers which are to decarbonise heat as well as electricity, which there aren't many ways to do that unless you use renewable electricity, of course. So let me close by actually saying, just giving you one example of the research I do. I do a lot on trying to make carbon capture and storage a reality. The technology that we have now can work, but we need to bring the cost down, and I'm working on making it more efficient and bringing the cost down. I work on this underground processing of CO2 so that maybe we'll have processes where we don't bring it up to the surface. And I also work on producing fuels like hydrogen from green algae and cyanobacteria, where you can use sunlight and water to produce hydrogen. We produce about a litre of hydrogen a day, which is not going to actually change anybody's lives. But to scale it is going to be difficult, but it is actually a way of going directly from sunlight to fuels without the need to use intermediate energies. So that's one of the links with the bio area. The other area where there's a link with medicine is a project that I've been the director of for some 10 or 12 years now. We're sponsored by the same region as Barcelona have been, so they've got good taste. This is a combination of sponsorship from Shell and Qatar Petroleum to look at carbon capture and storage in carbonate reservoirs, which a lot of the reservoirs of the Middle East are, compared with the sandstone reservoirs of the North Sea. And this is a very large project. It's £70 million over 10 years, which gives you time to really get to the grips with the problem and then see if it works in practice and go round the loop a few times. We quite like our logo, which is putting CO2 in its place. And one of the things that we do is to trap CO2 underground. You don't just pump it into a chasm and put a cork in. It's trapped there in porous media. And so you've got the seals that have kept the oil and gas in for millions of years. But you've also got capillary forces which make oil and gas difficult to get out. But once you get the CO2 in, surface tension keeps the CO2 trapped in the pores of the rock. And that's one of the things we've been working a lot on. We've had a lab that opened in the year of the Olympics, and we have 5 labs, so we have 5 Olympic rings. And I'm focusing on the yellow area, which is characterising the ways that fluids behave when you put them into these reservoirs. And the way you trap the CO2, which is the blue in that imaging photo, is, as I say, by surface tension, trapping it in there, surrounded by water, which makes the CO2 non-wetting to the rock, whereas the water wets it, and it's trapped there by surface tension. And these are some of my students that you can measure. An important thing here is the interfacial tension and the contact angle. You can see there that the droplets of CO2, supercritical CO2, makes with the rock surface. And that makes all the difference about whether it stays trapped or not. They're measuring these at the macroscopic level, so these droplets are a few centimetres in size. One of the revolutions at how you design oil and gas processes, and particularly storage processes now, is to use image analysis, which has been used in the medical profession for a long time. So this is a medical CAT scanner that you would normally have a body on the trolley there, and we put rock cores, and the only difference is that the X-ray beams that it goes through, we can put this at any angle. So oil wells are neither vertical nor horizontal, and we can tip that so that we go through the whole 90 degrees. This looks at, if you like, at the core scale of a few meters. We can also look down at the pores with a micro CT and see the CO2 that's trapped in the rock. And these different colours show the trapped CO2 on the left, and then when you flood it with water to trap it by these capillary forces, the different colours on the right are all CO2, but the different colours are how many pores are joined together. So these aren't isolated, they're sort of ganglia of CO2 ribbons. And I'm going to end by just showing you a video of what we've got is a small core of carbonate rock. We've trapped CO2 in it, and rather than measuring the contact angle at the centimetre scale, we're going to measure it at the micron scale inside this rock, which is where it really matters. And what I'm going to do is to scan up and down through this rock to see where the CO2 is trapped. And so we're going up and down, and the white there is the rock, the rock grains. The pores in between are filled with dark fluid, which is the CO2, and light fluid, which is the water. And now we've coloured that, so the rock is orange, the water is dark orange, and the CO2 is the blue there. And what we've now done is stripped away the rock. And what we have there is just that's the CO2 that is trapped in these continuous network of pores. And what we're going to do is we're going to look at the ganglia of CO2 that are in there, and we're going to try and isolate one of the droplets of CO2 to measure its contact angle. So as it strips away the rock and we look at the CO2 there, you can see that some of them are just almost spherical because they're in a single set of pores, and we can see that the different colours show how many pores are joined together. So the blue, a lot of pores, and the orange, it's only one pore. So let's just go in on that orange globule of CO2 that's trapped. And you can see that it's got flat edges where it comes into contact with the... So if I freeze it there, the orange is the rock. This is a slice across. The dark blue in the centre is the CO2, and the lighter blue is the water that's encapsulating it to keep it in the system. And what we're now going to do is to home in on that droplet of CO2, strip away the water as well as the rock, and you can see those flats on it, or where those yellow lines show where it's in contact with the rock surface. And then we can do some geometry to find out the angle it makes with the rock. And we want it to be more than 90 degrees to be non-wetting, and we need to know how that changes if we change the conditions in there to keep it trapped. And so what we're going to do is to freeze this at the point at which we do some geometry. There you can see that it's about 140 degrees, and this is significantly different than it is in the bulk experiments that we did earlier. So this shows that there's no substitute for actually going and looking in the rocks and understanding how the CO2 behaves to keep it there. That may be a long way from some of the political issues I've talked about, but the only way that we're going to actually bring this about is if we can bring the cost down and we have technology that's fit for purpose, and that we have policymakers that appreciate where that technology is going to make a difference in the chain. And so what I'd like to do is to leave you with some thoughts. There's plenty you can do. One thing that you might like to look at is how can you save 80% of your 10 tonnes of CO2 a year? And I'll leave the slides, you'll have the presentation. There's some calculators there produced by the government and other agencies where you can calculate your own carbon footprint and you can look at what effects you can have. And one of the things of using calculators like this, what you can see fairly easily is if we all became vegetarian, then the problem would disappear tomorrow, because methane from cows is, as I've said, far more dangerous than CO2. But we're not going to all be vegetarian. So I'll leave you with this thought, that there are no easy choices, there are no free lunches. Using fossil fuels and avoiding climate change is possible and it's compatible, but if we just continue to fiddle while Rome burns, then we have less and less time to make a difference and to actually get to our destination. Thanks very much for your attention.